540 Advanced Electromagnetic Theory and Antennas. I'm Professor Rakesh Singh Kshatriya. So in the last class we have discussed about the H-plane sectoral antenna, horn antenna. So in this class we'll discuss about the E-plane sectoral horn antenna. So this is the side view of the E-plane sectoral horn antenna. What are the changes? Let's see the feeding waveguide. This dimension will become now B, and the mouth of the horn antenna will have a dimension of capital B. And this is the neck of the horn antenna, this is the mouth of the horn antenna. The distance between the neck and mouth of the horn antenna will denote it by RE now, E for the E-plane sectoral horn antenna. Similarly, this flaring length also will denote it by LE. And this flaring angle also theta E. So this for the E-plane sectoral horn antenna, so we'll have LE, theta E, RE here. As usual, there are two coordinate system here. This is the y-axis, this is the x-axis, which is going into the computer screen, and this is the z-axis. Similarly, this is x dash, y dash, z dash, and this distance is y dash. Let's consider any position p dash in the mouth of the horn antenna. Now this distance would be y dash from the origin of the prime coordinate system. This is the face front, and this length from the face center to the mouth of the center of the mouth of the horn antenna will still denote it by R0 dash. But this R0 dash may be different from the R0 dash we have from the H-plane sectoral horn antenna. It is dependent on this LE theta E. If LE theta E changes, R0 dash will also change. Similarly, we'll still denote this distance between the face center and the point P dash as R1 dash. The path difference will denote it by delta. So let us try to analyze this E-plane sectoral horn antenna. This is the E-plane cut, YZ cut, E-plane YZ cut. As usual, the two dimensions required for construction of this E-plane sectoral horn antenna is capital B, and this would be B and RE. Once we know capital B, this is the dimension of the mouth of the horn antenna, and this distance between the neck and mouth of the horn antenna RE, we can construct this horn antenna in the left. Let us define what is the flare angle. Flare angle tan of theta E is opposite is B by 2, capital B by 2. Base is R0 dash. So if I want to find theta E should be 2 tan inverse capital B divided by 2 R0 dash. And this flaring angle at E square should be equal to B by 2 whole square plus R0 dash whole square. And the distance between the neck and mouth RE, which is one of the required dimension for construction of horn antenna, can be found out as capital B minus B square root of LE by B whole square minus 1 by 4. We can similarly derive it like last time when you have done the derivation for the H-plane sectoral horn antenna. We can do that. So what is tan of theta E? Tan of theta E is B by 2 divided by R0 dash. This is B by 2, this is R0 dash, this is tan of theta E by 2. Similarly, at this portion, what is tan of theta E by 2? That is small b divided by 2 R0 dash minus RE. This length is small b by 2. This total length is b, so this length is small b by 2. This length here is R0 dash minus RE. R0 dash is this length here, RE is this length here. So this distance from the face center to the neck of the horn antenna is R0 dash minus RE. So like last time we inverted and cancel the common term 2, then what we are getting is like this. We cross multiply it, we get like this. Simplify it, you get RE is equal to capital B minus B R0 dash by capital B. Again, you can replace this R0 dash in terms of square root of LE square minus B square by 4, then simplify it. This is the relation you have for the RE. From this relation you can find out what is RE. So we can also find out how much is the phase change or path difference for signal which has gone from this phase center to this point and this point. So this distance is R1 dash, this distance is R0 dash. I want to see the path difference. If I know the path difference, I know what is the phase change. So path difference is R1 minus R0 dash. You can use Pythagoras theorem. R1 dash is square root of R0 square plus y dash square. So this is R1 dash square, that is y dash square plus R0 dash square. So you take out R0 dash common, then what you have is 1 plus y dash by R0 dash whole square half to the power half. Use binomial expansion and take it up to the second term. This is what you have here. Transfer this R0 dash to the left hand side. You have the difference between R1 dash minus R0 dash is equal to 1 by 2 R0 dash y dash square. So this is the path difference of R1 dash and R0 dash. Once we have that, we can find out how much is the phase difference. So we'll denote this path difference by delta. Delta is, look at this expression for delta, it's in quadratic form. So people usually say that the change in the phase is in quadratic nature. So let us try to find out the fields radiated from this E-plane sectoral horn antenna. The first step is write down the fields in the aperture. So we can write down the field in the aperture now. Field in the aperture will have only Y directed fields, and its variation with respect to x will be E naught cosine of pi x dash by A. And we also have now this phase variation is exponential minus j beta. Delta was what? Phase variation will be exponential minus j beta. Delta is 1 by 2 R0 dash y dash whole square. So you can observe that this electric field has amplitude variation as E naught cosine of pi x dash by A. But phase variation is due to movement in the y direction, y dash direction. So amplitude variation varies with respect to x dash, but the phase variation varies with respect to y dash. Okay, so we have the aperture field. Let us try to analyze this aperture field with respect to different locations inside mouth of the horn antenna. How is the amplitude variation at E0 cosine of pi dash x by A? So if x dash is 0, that is the center of the mouth of the horn antenna, we have the maximum electric field. At the two edges, one is minus A by 2 and plus A by 2, you have 0 field here. How about the phase variation? Phase is varying with respect to y dash for different values of y dash. When y dash is 0, that is at the center or of the mouth of the horn antenna, we don't have any phase variation. This becomes 1. When you are going to the end of the mouth of the horn antenna, upper end and lower end, what you are seeing is that you have the maximum phase variation. Y dash will become minus b by 2 and plus b by 2. So the second step, as usual, is taking the Fourier transform of the aperture field, 2D Fourier transform of the aperture field. So let us do that. So 2D Fourier transform of the aperture field can be found out as integration of E0 cosine of pi x dash by A. You multiply by exponential j beta x dash dx dash, integrate it over the region minus A by 2 to plus A by 2. We have cleared out the horn waveguide to make the E-plane sectoral hole antenna only in the y direction. We have not cleared out it in the x direction. So the x limits will be from minus A by 2 to plus A by 2, but the y limit will be minus b by 2 to plus b by 2, capital B minus capital B by 2 to plus capital B by 2. So the phase variation was varying with respect to y dash, so exponential minus j beta 1 by 2 r naught dash y dash whole square. multiply by exponential j beta y dash, integrate it. So this integration is very familiar to us. We have done this derivation when we consider the open-ended waveguide, and it turns out to be 2 pi a cosine beta x by a cosine of beta x a by 2 and divided by pi square minus beta x a whole square. So this is a new integration. This integration turns out to be square root of pi r naught dash by beta exponential j beta r naught dash b square by 2 I1 theta comma phi. What is b? What is b? B is sin theta sin phi. What is I1? I1 is fs4 dash minus fs3 dash. We have already defined this f function. F function is actually c function minus js function. What is c and s? C and s are the cosine and sine Fresnel integrals. We have already discussed this. Mu is sin theta sin phi. What is S3 dash and S4 dash? S3 dash is defined as square root of beta by pi r naught dash minus b by 2 minus r naught dash b. S4 dash is, you just change the sign here. You take it, instead of minus plus here, you get S4 dash. So now we have the 2D Fourier transform of the aperture field for the E-plane sectoral horn antenna. Let us go to the third step. What is the third step? We use equation 27.1 and 27.2 to find the far field electric fields. Previously we used to use 24.1 and 24.2. For the horn antenna we have modified it, and I have called that two equations as 27.1 and 27.2. This is the expression for the electric field in the far field, theta component and phi component. They are very similar except for this sin phi and cos phi here. All other terms are similar. You have cosine variation 1 plus cos theta. This function, which is the 2D Fourier transform of the electric field, will also have theta variation. And this is the usual j beta exponential minus j beta r by 4 pi r. So we just need to plug in the 2D Fourier transform of the aperture field to get the electric field in the far field, theta and phi component of the E-plane sectoral horn antenna. Let us consider the particular cases when you have, let's say, E-plane or S-plane. In the E-plane, phi is pi by 2 is the YZ cut, YZ plane. When phi is pi by 2, look at this term here, this term will become 0, we'll have only this term, and sin phi will become 1. So the simplified expression is 1 plus cos of theta to the Fourier transform of the electric field. With this term here, phi component will become 0. What is 2D Fourier transform? 2D Fourier transform was expressed like this. So now let us try to find out the case when phi is equal to pi by 2. When pi is pi by 2, what happens to mu? No? We have a mu term here. Mu term is sin theta sin phi. So sin of pi by 2 is 1, it becomes sin theta. What happens to beta x? Beta x is also there. Beta x is beta sin theta cos phi, it becomes 0. So what happens to this term now? This term will become 1. This term will become 0. Let us look at this term here, especially this I1 theta comma phi. I1 theta comma phi was f of S4 dash minus f of S3 dash. What is S3 dash? S3 dash is this, S4 dash is this. So now here it was the term mu here. This mu here is sin theta sin phi. Now it will become just sin theta here. What happens to this term also? Mu will be simply replaced by sin theta square. So the final expression for the electric field in the far field for the E-plane turns out to be j beta a E naught exponential minus j beta r by 2 r pi square root of pi r naught dash by beta then exponential j beta r naught, this should be sine theta whole square by 2 into 1 plus cos theta fs4 dash minus fs3 dash. So now, what is the theta dependent term? Theta dependent term is this, and this. All are dependent on theta. Because here also you see S4 dash and S3 dash is dependent on theta. This is also dependent on theta. This term here is also sine theta. So this whole term will actually give you the field pattern of the E-plane sectoral horn antenna for the E-plane. But look at this term. If you want to find the amplitude of this exponential j beta, this term will become 1. That's why I have neglected it. If I am interested in the amplitude of the field, only these two terms, 1 plus cosine theta and fs4 dash minus fs3 dash term, will contribute in the radiation pattern of the E-plane sectoral horn antenna for pi is equal to pi by 2. So later on I am going to give you assignment to plot these radiation patterns. Similarly, we can also get the H-plane patterns. Phi is equal to 0. For the H-plane, we are considering exact cut of the 3D radiation pattern. In that case, look at the expression 27.1 and 2. When phi is 0, this term becomes 0, this term becomes 1, this cos phi becomes 1. We'll have only the phi component of the electric field in the far field for the H-plane. This is the expression for the phi component of the electric field in the far field for the H-plane. Let us try to find it out. So in this case, phi is 0, so mu will become 0. If mu is 0, this exponential term will become 1. Even this, you have I1 theta comma phi is a function of S4 dash and S3 dash, where this function is dependent on the cosine and sine Fresnel integrals. What you can observe is that S3 dash and S4 dash for this particular case, when phi becomes 0, is actually related. You see, S3 dash is square root of pi beta by pi r naught dash minus b by 2, but S4 dash is square root of beta divided by pi r naught dash plus b by 2. So S3 dash is equal to minus S4 dash. They are negative of each other. In that case, if I plug it in here, this term will be simplified as simply I1 theta comma phi is 2 times f S4 dash. Major simplification here. So the final expression for the 2D Fourier transform of the aperture field would be 4 pi a e naught x square root of pi beta r naught dash by beta cos of beta x by a, beta x a by 2 divided by pi square minus beta x whole square. Then this function here, f of S4 dash. So if we plug it in the expression of the 2D Fourier transform of the aperture field in the electric field in the far field of the H-plane sectoral horn antenna in the H-plane, pi is equal to 0, this is the expression you are getting. So you can see that this term is independent of theta. Only the term which is dependent on theta is 1 plus cos of theta cosine of beta x by 2 a by 2 divided by pi square minus beta x a. What is beta x? Beta x is beta times sine theta cos pi. So beta x is beta times sine theta cos pi. So when pi is 0, it will become just beta sine theta. So beta x is dependent on theta also. Beta x is beta sine theta. So this term will give you the radiation pattern for the H-plane sectoral horn antenna for phi is equal to 0. So we are also interested in the directivity of the H-plane sectoral horn antenna. It will have the same expression, similar kind of expression of the E-plane horn antenna. If you remember, the directivity was 4 pi by lambda square, efficiency due to taper in the fields, efficiency due to phase change, then area of the cross section of the H-plane sectoral horn antenna is small a into capital B. We have flare out only in the y direction, so B will become capital B, A will remain the same. So let us find out what is this epsilon taper and epsilon phase. So epsilon taper is standard for the open-ended waveguide. It's 8 by pi square, because we have already analyzed the epsilon taper for the open-ended waveguide, and that same field distribution is also here, cosine function with respect to x dash. So epsilon taper is 8 by pi square, which is approximately 0.81. Epsilon phase also you can find out by integrating the aperture electric field. Standard formula you have, it turns out to be c square q plus s square q divided by q square, where q is 2 times square root of s. So like last time when we consider the H-plane sectoral horn antenna, we have defined a new variable t. Here we'll define a new variable s. So how do we find this s parameter for maximum phase error? Where does maximum phase error occur in the mouth of the horn antenna? It's at the two ends, extreme end, one in the upper end and another in the lower end. So at the extreme upper end of the horn antenna, y dash becomes b by 2. We can take minus b by 2 also. Anyway, this is a square here, so it will become, we'll get the same value. So let's consider y dash is equal to b by 2. Then this is the phase maximum phase error, beta by 2 r naught dash y dash square. For the maximum phase errors, y dash will be either plus b by 2 or minus b by 2. You simplify it, it turns out to be 2 pi b square by 8 lambda r naught dash. You equate this maximum phase error to 2 pi s, then s will become b square by 8 lambda r naught dash. This is the value of s for the maximum phase error. So we have s, we can plug in and find out what is q. Once we have q, then you find out what is this epsilon phase. That is basically cosine Fresnel integral and sine Fresnel integral square of that, divided by q square. This is a cosine Fresnel integral square for q. This is a sine Fresnel integral square for q divided by q square. I will get the epsilon due to phase change in the mouth of the horn antenna. Once I have this, I have everything. I can find out the directivity of the H-plane sectoral horn antenna. The question is directivity dependent on B? Obviously it will be dependent on B. We have already seen that for the E-plane sectoral horn antenna also. And we have also what was one of the motivation for going for horn antenna from the open-ended waveguide was to increase the size of the aperture opening. So here we have flare out along the y-axis, so small b becomes capital B. So that value of b, capital B, will definitely affect the directivity of the horn antenna. So you can plot it, directivity of the horn antenna for different values of b, and it has been found out that the optimal value for the E-plane sectoral horn antenna, like that of the H-plane sectoral horn antenna, capital B, turns out to be square root of 2 lambda r naught dash. For this particular value of capital B, optimal value, we can find out what is the value of s. S turns out to be 1 by 4. So we know the value of s for the optimal value of the directivity. We can find out the optimal directivity. This is 0.81. This you can find out from this expression you have here. You already know what is value of s, 1 by 4. So you can 1 by 4, if you take square root, q will become 1. So you can find out this. You have the epsilon due to phase changes in the mouth of the horn antenna. This is the area of the aperture opening of the horn antenna, which is a into capital B. So you can find out the directivity of the horn antenna. That's all for this class. We'll discuss about the pyramidal horn antenna in the next lecture. Thanks for your attention.